Hi everyone. In earlier videos, we saw clustering in, in earlier videos, we saw clustering in multimedia, time series data, and clustering test data, and clustering in categorical data. Now we are going to see clustering in discrete sequence. Clustering discrete sequence. Many forms of data create discrete sequence instead of categorical ones. For example, web logs, the other command series sequence in computer system and biological data are discrete sequence. The contextual attribute in this case often corresponds to placement. Example, biological data rather than time. Biological data is also one of the most common application of sequence clustering. As with the case of continuous sequence, the key challenge is the creation of similarity functions between different data objects. Numerous similarity functions such as Hamming distance, edit distance, and longest common sequence are commonly used in this context. A discussion of the similarity functions are commonly used for discrete sequence. Uh, discrete sequence may not be found in. Another key problem which arises is in the context of clustering discrete sequences that are intermediate and a summary representation of a set of sequence can be computationally intensive. Unlike numerical data where averaging methods can be used, it is much more difficult to find representation for discrete sequence. A common representation which provides a relatively limited level of summarization is the suffix tree. Methods for use suffix trees for sequence clustering methods have been proposed in CLU clustering sequence. For CLU, this case abbreviation is clustering sequence. As with the other case, unlike numerical data where averaging methods can be used, it is much more difficult to uh, find such representation for discrete sequence. Generative models can be utilized both to model the distance between sequence and to create a probabilistic model of cluster generation. A particularly common approach is the use of mixture of HMMs, which means the abbreviation of HMM is hidden Markov models. A premiere on hidden Markov models may be found in hidden Markov models can be considered as a special kind of mixture model in which the different components of the mixture are dependent on one another. A second level of mixture modeling can be used in order to create clusters from these different hidden Markov models. Much of the work on sequence clustering is performed in context of biological data. This is clustering in discrete sequence. Now, clustering in network data. Graphs and networks are among the most fundamental and general of all data representation. This is because virtually every data type can be represented as similarity graphs with the similarity values on the edges. In fact, the method of spectral clustering can be viewed as the most general connection between all the other types of clustering and the graph clustering. Thus, as long as similarity function can be defined between arbitrary data objects, spectral clustering can be used in order to perform the analysis. Graph clustering has been studied extensively in the classical literature, especially in the context of the problem of two-way and multi-way graph parsing. The most classical of all multi-way parsing algorithms is the Kernighan-Link method. Such methods can be used in conjunction with the graph coarsening methods in order to provide efficient solution. These methods are known as multi-level graph partitioning techniques. A particular popular algorithm in this category is METIS. METIS. A number of methods are commonly used in literature in order to create a partition from graph. Generative models, as discussed earlier, it is possible to define a generative model for practically any clustering problem as long as appropriate method exists for defining each component of the mixture as a probability distribution. And an example of a generative model of network clustering is found in later you can see the examples. Classical combination algorithm. These methods use network flow or other iterative combinational technique in order to create partition from the underlying graph. It should be pointed out that even edge sampling is often known to create good quality partition. When it is repeated many times, it is often desirable to determine cuts which are level balanced across different partitions, because the cut with the smallest absolute value often contains a large majority of the nodes in a single partition and a very small number of nodes in the remaining partition. Different kinds of objective function in terms of creating the cut, such as the unnormalized cut, normalized cut, and a radial cut, provide different trade-offs between cluster balance and solution quality. It should be pointed out that since graph cuts are combinatorial optimization problem, they can be formulated as integer programs. Spectral methods. Spectral methods can be viewed as linear programming relaxation to the integer programs, representing the optimization of graph cuts. Different objective functions can be constructed for different kinds of cuts, such as unnormalized cut, radio cut, and normalized cut. Thus, the continuous solution to these linear programs can be used to create multi-dimensional embedding for the nodes on which conventional k-means algorithm can be applied. These linear programs can be shown to take an especially convenient form in which the generalized eigenvectors of the graph Laplacian correspond to solution of the optimization problems. Optimization problems. Non-negative matrix factorization. Since a graph can be represented as an adjacency matrix, non-negative matrix factorization can be used in order to decompose it to low rank matrices. It is possible to apply the matrix factorization methods either to the node adjacency matrix or the node edge adjacency matrix to obtain different kind of insights. It is also relatively easy to augment matrix with the content to create analytical method which can cluster with a combination of content and structure. While the aforementioned methods represent a sampling of the important graph clustering methods, numerous other objectives are possible for the construction of GraphQL, such as the use of modulatory based objective function. Furthermore, the problem becomes even more challenging in the context of social network may be available at either the nodes or edges. Now, clustering in uncertain data. We already see categorical data, test data, multimedia, time series, discrete network. Now uncertain. In uncertain, many forms of data either are of low fidelity and the quality of the data has been intentionally degraded in order to design different kinds of network mining algorithm. This has led to the field of probabilistic database. Probabilistic data can be represented either in the form of attribute-wise uncertainty in the form of possible worlds model, in which only particular subset of attributes can be represented in the data at a given time. The key idea here is that incorporation of probabilistic information can improve the quality of data mining algorithm. For example, if two attributes are equal desirable to use in an algorithm in the deterministic scenario, but one of them has greater uncertainty than the other, then the attribute with less uncertainty is clearly more desirable for use. Uncertain clustering algorithms have also been extended recently to the domain of streams and graphs. In the context of graphs, it is often desirable to determine the most reliable subgraphs in the underlying network. These are the subgraphs which are the most difficult to disconnect under edge uncertainty. With here, we finish data types studied in cluster analysis. These are preface of this, and we will explain detail about this. First, clustering uncertainty. We complete common techniques used in cluster analysis, data study, cluster analysis. With here, and in next I will talk about insights, which is in that visual insights, supervised insights, multi-view insights, multi-view and ensemble based insights, validation based insights. These are combined in this. In next video, we will make it so. Thank you.